Variation of current with frequency. So x-axis is frequency, y-axis is current, and we have the expression for current as I is equal to V by R Z. Okay, V by Z. So where Z is equal to R plus J XL minus XC. Okay, so here we have Z is equal to R. We have R Z is equal to R plus J XL difference XC, and current is given by I is equal to V by Z. So we are writing expression, we are writing a graph of current versus frequency. It is a variation of current for different values of frequency. Okay, I already told that XL is equal to what? Omega L. X is equal to 1 by omega C. As frequency increases, omega increases. As frequency increases, XC, reactance of the capacitance, decreases. So in the initial portion, what happens? Okay, we start from frequency varying from 0. When you keep on increasing, omega L is increasing, but in this portion, okay, Xc is very high, much greater than XL. Xc is greater than XL, and at this particular frequency FR, Xc is equal to XL, circuit behaves as resistance, and for very high frequencies, Xc is actually less than XL because it is directly XL is directly proportional. As frequency increases, XL also increases. Since for Xc it is inversely proportional, as F increases, Xc decreases. So Xc is less than XL for higher frequencies, and Xc is greater than for lower frequencies. Xc is greater for higher frequencies. Xc is lesser. And at FR, at resonance frequency, Xl is equal to, so, and circuit resistance is only circuit impedance will be only purely resistance at resonance frequency. So at here at I max, we are going to get I max when the impedance is equal to purely resistance, which is R. So here circuit impedance is only R. So here some reactance will be there. So that's why you will get less. Current will be maximum when circuit impedance is only R. If any other is there, so actually we are dividing with increased denominator. Okay, because Z we have to consider R plus this term also. So current will decreases. Current is maximum when Z is equal to R only. Now we have to consider two more points in the frequency response. So let us call it as half power frequency. Here at this point, P is max. Okay, this point is called as when current is maximum, power is also maximum. When you're considering a bandwidth of any circuit, we have to consider at least the waveform should have half of the minimum maximum power. Suppose this is the maximum power. Here you have to consider the all the frequencies. At least the power should be half of that. So let us consider these 2 points as P max by 2. Okay, it's called as half power frequencies. F1 and F2 are also called as half power frequencies. F0 is maximum. It is maximum power is available at the resonance frequency, and F1 and F2 at least you are getting half of the maximum power. So when we know that power is given by V into I. Okay, power is equal to V into I. So at here at I and I max, the current value is given by I max by root 2, because if you take I square into R, then I square, if you take I max by root 2 whole square, it becomes I max square into R only you are going to get. So that I will explain here later. So impedance of the series circuit is given by R plus J XL minus 1 by XC, omega L minus 1 by omega C, and the magnitude of impedance is given by root of R square plus omega L minus omega C whole square. At resonance frequency, XL is equal to XC, it will get cancelled. So the magnitude of impedance becomes R, and circuit behaves as purely resistive circuit. This I already explained in the resonance also. And impedance offered by the circuit is minimum because Z is equal to only R. We don't have reactance part. And current is given by V is equal to R. Okay. And this current we call it as I max. So let us, instead of I, let me call it as it is I max. So I max is given by V by R only. Now, figure shows the frequency response of this RC circuit with varying supply voltage be constant. The frequency F1 and F2 corresponding to I max by root 2 are called as cutoff frequency or band frequency or off power frequencies. So F1 and F2 where power is equal to half of the maximum power, we call it as off power frequency or cutoff frequency or band frequency, and the difference between F2 and F1 is called as bandwidth. The frequencies F1 and F2 are also called as off power frequencies because power in the circuit at these frequencies half of the maximum power. That's what I told. And power Pmax is given by Imax square into R. Okay, at resonance, circuit behaves like a resistance only. So current is at that point is Imax. So power is given by V into I, where V can be written as I into R. So Imax square into R. Okay, power is given by voltage into current, and it is maximum. Okay, V is equal to Im into R plus Im. It is Im square into R. So P is equal to current into voltage. V is equal to given by I into R. Im into R. Im square into R. I max into R. P max is Im square into R. And at top 4 frequencies, okay, let us consider P max by 2. Okay, at P max by 2, if at P max by 2 means, okay, P max by 2 means Im square, Pm by 2 means I max square into R by 2. So this I can write as I max by root 2 whole square into R. I max square into, if you take I max by root 2 whole square, Im square will get, and root 2 into root 2 is 2 you are going to get. So it is I max square into R. So what you'll understand from this, at F1 and F2, okay, we have half power. Power is given by this, and current value is equal to I max by root 2. So in this graph, at this point, current is I max. At these two, power is off, and current value becomes I max by root. This value divided by root. And bandwidth, sometimes they'll ask definition. They'll ask for 8 marks. Define following terms. What is resonance frequency? You have to write resonance frequency is the frequency. Okay. Uh, we have this definition now. You have to write resonance is a frequency at which XL is equal to XC, and expression for FR you have to write. There is a definition for resonance frequency. And they'll ask define bandwidth. Bandwidth is the range of frequency between two cutoff frequency. F2 minus F1 is the bandwidth of the circuit. Or you can also write it is the range of frequencies. That is a difference between F2 and F1. Where F2 and F1 are nothing but cutoff frequencies. Okay, they are nothing but half power frequencies. F1 and F2 are half power frequency, and difference between F2 and F1. That is F2 minus F1 is called but bandwidth. So in this graph, this width, this is lower cutoff frequency. This is upper cutoff frequencies, and middle one is resonance frequency. Okay, the difference between F2 and F1. Difference between F2 and F1 is nothing but bandwidth. BW means bandwidth. Next, variation of impedances with frequencies. Okay, variation of impedances with frequency. Again, Z is equal to, here this is Z. Okay, this is a Z. Y axis is Z. This is frequency F. So again, I already told, as frequency increases, reactance of inductance and capacitance is going to vary. So you are not going to get constant throughout the frequency if you vary the frequency. At resonance frequency, omega XL is equal to XC, and they will get cancelled. Circuit behaves as purely resistance. Z magnitude of impedance is given by root of R square plus, before that, what is Z? Z is given by R plus J XL minus XC. Okay, XL minus XC, and magnitude is given by root of R square plus XL minus XC whole square. So at resonance frequency, at f is equal to fr, xl is equal to xc. They will get cancelled each other and magnitude is equal to only r. So at resonance, okay, at resonance, the value of z is minimum, but current is maximum. Z is minimum because we have only this part. We don't have this part. Okay. And in this portion, for the lower frequencies, your XC is greater than XL, and for higher frequencies, XL is greater than XC. Here, capacitor reactance is less, inductive reactance is more. Here, capacitor inductance is less, inductive reactance is less. So this is because this is directly proportional. Omega is 2 pi FL. This is 1 over 2 pi FC. It is indirectly proportional. So in all the portions other than resonance, we have only R, and in other parts we have this part also will be there. So that's why here you are going to get R plus JXL minus XL difference XC. Here also you are going to get R plus JXL minus XC. At only this point, your Z is equal to only R. So this is the variation of impedance with frequencies. And one more important question they are going to ask in the definition for this one is they will ask resonance frequencies, bandwidth, and one more is quality factor Q. So it is a ratio of inductive reactance or capacitive reactance to the resistance of the circuit. It is equal to Q is equal to Q is equal to react inductive reactance, that is omega L by R. Okay, omega L by R. XL means omega L by R 1 over omega C R. You can write this one. Or you can also have another definition for Q. I'll show you that the definition for Q is it is ratio of, you can also express quality factor as it is a ratio of resonance frequency divided by bandwidth. Resonance frequency by bandwidth. You can write this definition or you can write this definition. Both are correct. Okay. It is omega L by R or capacitive reactance by resistance. It is defined as the ratio of inductive resistance or capacitive reactance at resonance to the resistance. So how to express quality factor? Another formula. You can for the formulas you require this formula. You require this one more formula. So QS is given by omega L by R. It is at resonance. Omega is represented as omega R. So 2 pi F omega is 2 pi F R into L by R. It is reactive inductive reactance by R. We are considering inductive reactance by R, but FR is given by 1 over 2 pi root LC. That is resonance frequency for series RLC circuit. Okay, you substitute FR is equal to 1 over 2 pi root LC. Then 2 pi will get cancelled. 2 pi will get cancelled. And this root L, this L can be written as root L into root L. This L can be written as root L into root L. This L can be written as root L into root L. In that root L will get cancelled. We left with root LC. So root of L by C will come. Root of L by C will come and this denominator R will be there. So 1 by R root of L by C. This is also one of the formula for quality factor. Quality factor is given by 1 by R root of L by C. So I will repeat once again. Q factor in terms of RLC is it is inductive. You can start from inductive capacitive inductance by R also you can take. There also you'll get the same answer. So omega R L by R, where omega R is 2 pi FR. We know that for series resonance factor, for series resonance circuit, FR is given by 1 over 2 pi root of LC. You substitute that 2 pi will get cancelled. This L you write root L. So root L will cancel with root L. We left with root L in the numerator. C also there. Root of L by C into 1 by R. So this is Q factor in terms of RLC. So another important definition term is Selectivity. Define selectivity. Four terms they will ask. It is for 8 marks. So define selectivity. Selectivity of a series resonant circuit is defined as the ability of a circuit to distinguish between desired and undesired frequency. Okay. Selectivity of a series resonant circuit is defined as the ability of circuit to distinguish between desired and undesired frequency. So here you can see think I will explain later. Okay, bandwidth. No, here you can take circuit. For example, this is a bandwidth. So how to find the frequency response? No, so if I want, this is a bandwidth is f2 minus f1. If the selectivity is good, okay, this bandwidth should be less. If you have like this response, then selectivity is more. If this is like this, selectivity is not good. So selectivity means I want only half of frequency means only this range I have to select. I should not select any other frequency. So for selectivity, it is resonant frequency defined as the ability of a circuit to distinguish between desired. Desired means within a bandwidth. Okay. Undesired frequency means out of bandwidth frequencies. So it is the ability of the circuit to distinguish which one is desired and which one is not desired. So that is the definition for selectivity.